Well, thank you very much, and good afternoon. I am very grateful to be here, and certainly thank Himanshu for the invitation to talk to you at my inaugural visit to ICCE. I think based on some of the presentations that I've seen today, I certainly do imagine that there's a role here for quantum computing in the future. I know that one of the topics on everyone's mind is, when is that actually going to take place? And so instead of trying to answer that question, which I think is very difficult right now, I'm going to try to address the question of why I think quantum computing is going to have some impact on the energy and cybersecurity aspects of consumer electronics in the future. For those of you who don't know, Oak Ridge National Laboratory is a Department of Energy research and development facility. It largely focuses on basic science research. The 4 areas that you see here typically translate ideas over into other technologies such as consumer electronics. In particular, we've been working on quantum computing now for over a decade, looking specifically at how it can impact scientific computing and high-performance computing, but I'll try to detail to you some of the ideas that we've come across that likely have applications in a broader space, such as consumer electronics. Himanshu told me I had about 5 slides. So somehow I've got to teach you quantum computing within this time. I'll do my best, but I'm going to leave out a lot of the details. And in fact, the answer to this question, what is quantum computing, is entirely on this slide. So at the heart of it, quantum computing is doing computation using quantum mechanics. If you're familiar with the idea of the Turing model of computation, imagine a quantum Turing model. Essentially, quantum mechanics says that there is a wave function that serves as the state variable for a quantum computing system. Computation then involves transformations of that state variables according to specific logical sequences. Now, it's a little unintuitive. If you see in the top right diagram here, it's the typical picture of the hydrogen atom that we've all learned in grade school. There's a center, which is the nucleus, and then there's an orbit, which contains the electron. But the picture you see down at the bottom is an actual image taken of a hydrogen atom, and it looks kind of like what we've learned. But the truth is, this is the wave function, a diffuse representation of information. It has interference effects, it has superposition effects, it even has random effects that quantum mechanics all says should be there. Quantum computing takes advantage of those to try and accelerate computation, specifically come up with faster ways of solving the same types of problems that we're familiar with. Here are some examples of problems and applications that we have identified where quantum computing can make a significant impact. In this top listing, you'll see specific problems that we know quantum computing works well for. Simulation, calculating partition functions, which is essentially summation, doing discrete optimization, training for machine learning, factoring numbers, searching unstructured databases, solving eigensystems, as well as other linear systems. And this isn't the complete list, but these are the ones that I thought would be most relevant. Now at Oak Ridge, we're largely interested in this in terms of scientific computing, specifically physical domains that can motivate these types of applications. So high energy physics, computational chemistry, artificial intelligence shows up here largely for data mining and scientific discovery, but also planning and routing and verification and validations of logical systems. Now, these types of applications I don't think necessarily translate directly into the types of consumer electronics that I'm concerned with, but they certainly serve as the backbone for those basic scientific discoveries that we're going to need to make advances in materials, engineering, and computing. Instead, I'd like to talk to you about 4 of the particular applications that I think do have a more immediate impact. And the first of these at the top left is in the field of secure data processing. Now, unfortunately, the lines in these diagrams don't show up very well, so I'll try to outline exactly what's going on here. Instead of showing you what a real quantum computer looks like, and I'll get to that at the last slide, I'm using this notation of a queue just to give you an idea of that system. Here you can see a paradigm where there's a doctor who's maybe ordered some diagnostics on her patient. Those diagnostics are shared, of course, over the cloud, but the question is, what's that data and how is it processed to provide information to that doctor? In this case, blind quantum computing is a paradigm in which the data itself can be encrypted, the computation that the doctor orders on that data can be encrypted, and what's even more important, the computer that carries out that computation has no idea what it actually is doing. Hence the blindfold around the system. Now in this case, there's actually a way to certify that the computation has occurred securely. Both the patient and the doctor can get access to this information. This, of course, depends on the implementation, and if there is, for example, a flaw in the implementation, then this will become aware during the certification process. Now, in a related concept, as I mentioned earlier, searching unstructured databases is another application of quantum computing, certainly in an Internet of Things where the end users are requesting access to information that may not yet have been categorized or structured. The ability to quickly parse through those lists actually can have an advantage. But again, this looks more like a remote cloud-based service as opposed to a service on the device itself. On the top right corner, you'll see the improved inference. This is a case where we know quantum computing actually can boost the training accuracy in typical machine learning applications. And so here the quantum system has to ingest the input data, form the inference relationships, and then train these neuromorphic processors on their representation of that. And then finally, I couldn't resist the opportunity to point out that quantum computing also can offer better odds in Las Vegas. Of course, quantum computing is well known for having a feature of randomness in its operation, and we've used this recently to demonstrate random number generation. I think what has struck me most about being here in Vegas is the sheer number of people who have to understand mathematics to get by here. They call them dealers, but really I just see mathematicians standing behind those tables. This is essentially the areas where I see quantum computing in the near term having applications for consumer concerns, but there is, of course, the question of, well, how far away are we from realizing those applications? And so this is a summary of the current status of quantum computing hardware. Up until last week, I would have told you that IBM and D-Wave were probably one of the two leading vendors for providing quantum processing units. But of course, as many of you may have known, Intel made an announcement at the CES show that they also have demonstrated a quantum processing unit, this one up to 49 qubits. So that's quite a remarkable demonstration. These processors are devices that we can actually program. We can run small-scale demonstrations on. We use those for solving scientific problems. We can do the same for solving the problems that I described a second ago. However, most of these have on the order of 50 bits of input data that they can accept. There's an article out this week on the Next platform which says that quantum computing right now is around the time of 1968, which is about when conventional processors made a transition into what they call their medium size configurations. So whether or not that's accurate, whether it's really 50 years from now that we need to wait for quantum computing to be as powerful as conventional methods, I don't know. My expectations are within the next 5 years we'll see some niche applications using these quantum processing units, and then of course it will continue to grow after that. So thank you all very much for the opportunity to speak.
Panasonic.